Good day, everyone. Welcome to another episode of CHE 101. I am Joven Reyes, here to discuss Feature 1, specifically real gases. But first, what are real gases? Real gases occur in high pressures and low temperatures, and they do not obey the ideal gas law. What's different is that real gases are affected by the intermolecular forces of the atoms, and it also takes into account the volume occupied by the gas molecule. An important concept is the compression factor, which is Z equals to Vm over V naught m. Vm represents the molar volume occupied by the real gas, and V naught m represents the molar volume occupied by the ideal gas. When PV equals nRT is added to the formula, you can get Z is equals to PVm over RT. When the value of Z is equals to 1, it means that it is an ideal gas. If Z is greater than 1, it occurs on high pressures. This means that the repulsive forces is dominant in the real gas. If Z is less than 1, it occurs on intermediate pressures and attractive forces are dominant. Now, we would go over the different equations of state. First up, the virial equation, which is PVm is equals to RT times 1 plus B prime P plus C prime P squared and so on and so forth. This is also equal to RT times 1 plus B over Vm squared plus C over Vm squared and so on and so forth. If you would observe the things in the parentheses, these are series, and the virial equation becomes more and more accurate as more terms are added. And take note that the things in the parentheses is also equal to the Z or the compression factor of the gas. Next is the van der Waals equation, which is P is equals to RT over Vm minus B minus A over Vm squared. For this equation, this has the correction to take into account the intermolecular forces and the volume occupied by the gas. The term A over Vm squared corrects for the intermolecular forces of attraction, while the term Vm minus B corrects for the volume occupied by the gas. Third is the Berthelot equation, which is used when the pressure is usually 1 atmosphere or lower. It is P is equals to RT over Vm minus B minus A over T Vm squared. And lastly, the de Ricci equation, which is typically used when the values are near the critical values. It is P equals to RT over Vm minus B times E raised to negative A over RT Vm. Let us have a sample problem. Calculate Z and Vm for steam at 250 degrees Celsius and 1800 kilopascal using the virial equations of state. Constants are B is equals to negative 152.5 centimeters cubed per mole, and C is equals to negative 5,800 centimeters to the sixth power over mole squared. To solve this problem, let us input our given. For pressure, we have 1,800 kilopascal, but we can convert this to pascal so that things would cancel out later, which is 1,000 pascals per 1 kilopascal times Vm equals R with a value of 8.314 pascals meter cube per mole Kelvin, but we must also convert this to centimeters cube, or rather centimeters, as R given is in centimeters. So 1 meter and then 100 cm, and then raised to cube, cancel things out, times 1 plus B, which is negative 152.5 over Vm, plus C, negative 5,800 over Vm squared. Now we may use the shift solve function of our calculators to get Vm equals to 2249.83 centimeters cubed per mole. That would be our final answer for Vm. To solve for the value of Z, we have a lot of different approach. One approach is to use the things in the parentheses as this is equal to Z. So Z is equals to 1 plus B, which is negative 152.5 over Vm, which is 2249.83 83 plus C, which is negative 5,800 over 2249.83 squared. We will get a value of 0.9311. Another method is to use the Z equals to PVM over RT formula. So to you viewers at home, try answering this using the Z equals to PVM over RT formula and see if you will get 0.9311 as your final answer. Another concept is the critical constants. Beyond these points, no liquid can condense. And the matter beyond this point are called supercritical fluids. Supercritical fluids have both the properties of gases and liquids. They have the solvating power and density similar to a liquid, while also having the diffusivity and low surface tension of gases. For the van der Waals equation, here are the values of the critical constants. For the critical pressure, it is equal to A over 27B squared. For the critical volume, it is equal to 3B. And lastly, for the critical temperature, it is 8A over 27 BR. You may ask, do we need to memorize these things? Thankfully, if you know your Cal Eng 1, you can just derive it from the original equation. To start off, let us label the original van der Waals equation, equation 1. Next, let us derive the van der Waals equation with respect to Vm to get dp over dvm is equals to negative RT over Vm minus B squared plus 2A over Vm cubed. Let us equate this to 0. Since if you would look at the graph, the critical point is a turning point in the graph of the function. Let us label this equation 2. Let's now get the second derivative of this equation. So we have the second derivative is equals to 2RT over Vm minus B cubed minus 6A over Vm to the 4th. And we can also equate this to 0 as it is also an inflection point. Let us label it equation 3. Now that we have these three equations, let us manipulate equation 2 so that we can have a better visual. So RT equals to Vm minus B squared is equals to 2A over Vm cubed. That is equation 2. For equation 3, we have 2RT over Vm minus B cubed is equals to 6A over Vm to the 4th. Now, let us manipulate equation 2 and equation 3 so that we could equate one to the other. What we could do is we could multiply equation 2 by 3 to get 3RT over Vm minus B squared equals 6A over Vm cubed. And then for equation 3, we could multiply the entire thing by Vm to get 2RT Vm over Vm minus B cubed equals to 6A over Vm cubed. We can now equate these two terms together to get 3RT over Vm minus B squared is equals to 2RT Vm over Vm minus B cubed. So now we could cancel out R, we could cancel out T, and we could cancel out Vm minus B squared and the cube. We will get 3 is equals to 2Vm over Vm minus B, and we could cross multiply to get 3Vm minus 3B is equals to 2Vm, and then transposing 2Vm to the left side and 3B to the right side to get Vm is equals to 3B, which is our first critical constant. To get the value of our second critical constant, we can substitute the value of Vm is equals to 3B in either equation 2 or equation 3. Let us substitute it to equation 2. So RT over 3B minus B squared is equals to 2A over 3B cubed. Let us expand that to get RT over 2B squared, which is 4B squared, is equals to 2A over 3B cubed, which is 27B to the cube. We could cancel out B squared and the cube, to get RT over 4 is equals to 2A over 27B. And now let us put all things to the right side to get TC equals to 8A over 27R, which is our second critical constant. To obtain our last critical constant, let us first move all our solutions so that we would have more space. And let us start. To solve for our last critical constant, let us substitute VC and TC to equation 1. So PC, signify that it's critical, is equals to R over Vm minus B, which will be 3B minus B, times T, which is 8A over 27RB, minus A over Vm squared, which is 9B squared. So let us cancel out R and simplify the first term to get 8A over 54B squared minus A over 9B squared. Let us convert that to one fraction, so 54B squared as denominator, 8A minus 6A, which is 2A over 54B squared. And to simplify, we have A over 27B squared, which is our last critical constant. For more practice, you could try solving for the critical constants of the Dieterici and Berthelot equations. Now, let us have our last sample problem. Calculate the mass of methane in a 260-liter cylinder at 0 degrees Celsius and 100 atm, assuming methane obeys the van der Waals equation. The critical temperature is equal to 190.6 Kelvin, and the critical pressure is 45.99 bar. To solve this problem, we must first solve for the values of A and B. We can use PC and TC for that. So PC is equals to A over 27B squared. We could multiply the whole thing by 27B to get 27B PC is equals to A over B. For TC equals 8A over 27BR, we could multiply the whole thing by 27R over 8 to get 27R TC over 8 is equals to A over B. Now we could equate these two terms to each other. So 27B PC equals 27R TC over 8. And then we could cancel out 27 and then transpose PC to the other side to get B is equals to R PC PC over 8. Now, we could transpose PC to the other side to get B is equals to R PC over 8 PC for B. Now to get A, let us just substitute it to the one of the original equations. So let us use PC. So 27B squared PC is equals to A, so A equals to 27R squared PC squared over 64 PC squared times PC, which will be equal to 27R squared PC squared over 64 PC. Let us remove all of this so that we would have space for the problem. So A equals to 27R squared PC squared over 64 PC, and B is equals to RTC over 8 PC. To get our values of our van der Waals constants, we could just substitute the values. So A is equals to 27. For R, we could use the value of 0.08205 as we have values in liters and in atmospheres. 0.08205 squared times TC of 190.6 all over 64 times PC, which is 45.99. However, it is expressed in bar. So we could divide it by 1.01325 to express it in atmospheres to get a value of 2.273. And for B, Let us substitute R is equals to 0.08205 times a TC of 190.6 all over 8 times BC of 45.99 over 1.01325 to get a value of 0.04307. Now that we have these values, we can now use the van der Waals equation to get the mass of methane. So 100, which is our pressure, is equals to N times 0.08205 times 273.15, which is our temperature, which is 0 degrees Celsius, all over 260 minus N times 0.04307 RB minus 2.2738, which is our A, times N squared all over 260 squared. We will get a value of N, or the number of moles, of 1569.71 moles, and using the molar mass of methane, which is 16.05 grams per mole, we could get our final answer of a mass of 25,193.85 grams as our final answer. That marks the end of our CHE 101 episode. If you have any questions, you may contact the chen.acads Gmail or the chen.acads Hub Facebook page. That is all. Thank you for watching.